welcome you all to this group theory Sangam talk. I'm happy to introduce to you Professor Mahan Maharaj, today's speaker. He's a professor of mathematics at Tata Institute of Fundamental Research, Mumbai. And today he's going to speak on percolation on hyperbolic groups. Professor Mahan MJ, over to you.
Yeah, thank you. Thank you very much for this invitation and this opportunity to talk about this stuff. So all that I'll be talking about is joint work with Riddhipratim Basu from ICTS. Okay, so I think, yeah, maybe I think there's some mic which is on, which is giving a little feedback. All right. So first I'll define what the terms are. Yeah. So what is percolation? And the model for percolation is quite simple. I mean, essentially what it means is that, say, take a point on the floor and you keep splashing water on it, and you basically ask statistically or probabilistically how long it takes to reach another fixed point in your on the floor. So how to formalize this? And the way one formalizes is the following. So let me see if I can do this better. Okay, good. This is better. Yeah. So so you start with a graph whose vertices are given by V and edges by E. And your probability distribution, and there's a certain probability distribution which you should think of as a way of assigning lengths to your edges. Yeah? So for the purposes of this talk, these lengths will be strictly in 0 and infinity. Yeah. So there is an extra possibility which one also is occasionally interested in allowing, which means basically that the edge is not there, so you can allow infinity also, which is why I have put this 0, infinity with a close bracket at infinity. But for the purposes of this talk, we are just going to allow lengths to be some positive real number. Okay. So what does that mean? Essentially, it means that given an edge, you are assigning a length to it according to the probability distribution on R plus. Fine. Now, the thing is, okay, so this is for a single edge. How about for the entire edge set? And you do the naivest thing possible, which is basically you take R plus equipped with this probability distribution, that's this R plus comma rho on the next line, and you just take a product of this probability measure, which is a product of R plus comma rho with itself, one for every copy of the edge, one copy of this R plus comma rho for every edge. Yeah. So which means basically R plus comma rho product with itself mod E many times. So we'll be essentially where this blackboard E is the same as the script E that we do upstairs. Yeah. So essentially we are going to be interested in the case where the edge set is infinite. So which means typically you're going to take an infinite product of R plus with itself, equipped with this probability distribution rho. All right. So now you assign a certain random variable. What does that random variable do? Your total probability space is omega equipped with this product probability measure, which is denoted by this P with the blackboard font. And so what does the random variable do? It eats a point of your probability measure space and spits out, so an element of this capital omega of your total probability measure space, an element is denoted as little omega. And so what does little omega do? It assigns a length to every edge. So essentially omega is a function on the edge set. Little omega is a function on the edge set which assigns to every edge little e belonging to capital E a length in R plus. The random variable xe works differently. It eats a point of the probability measure space and spits out the length of that specific edge. Yeah? So that's how it functions. Yeah. So that's And essentially, once you do that, this xt is just going to assign for you as your little omega varies over your probability measure space capital omega. It's just going to give you lengths of the specific edge e, and the probability distribution that you get for that edge little e is the probability distribution rho that you started off with. Okay, so this object, essentially, what does it do? You think of, you have a measure space at the bottom, which is your capital omega, and then you look at your little e as an edge, which now is parameterized by your little omega belonging to capital omega. So if you want to think of this as a bundle, the base is this probability measure space, and the fiber is this edge, and the edge length keeps varying depending on which little omega you're over. Yeah. So this length of edge E parameterized by your probability measure space capital omega is what you're going to call a random length of the edge E, or the random length of edge E. So the random length, when we use this language, say that the random length of an edge E, we don't mean a specific length, we mean lengths, all of them parameterized by your probability measure space. So your base is capital omega, fiber is little e. Now, instead of making the fiber little e, you could make that some edge path. So take some edge path gamma in your underlying graph, capital gamma. So what is an edge path? This is an E1, E2, Ek, so that the final vertex of E1 is the beginning point of E2. So then what does each little omega belonging to this total space do? It assigns for you the length of that path. Okay? So now you can actually think of gamma as parameterized by capital omega. And what does it do? For every little omega, just a moment. So for each little omega, you're going to assign a length to this gamma by just summing over the random lengths that you had in the first place. Yeah. So each geometric object, we started off with an edge, and we let the point in the parameterization space omega vary, and we got a variable, we got a family of lengths. Yeah. One for every little omega. So omega was assigning a length for every edge. Now what is little omega doing? It is eating, instead of an edge, it is eating an edge path, and it is spitting out this summation of omega e belonging to that edge path. So each gamma is now giving a random length of gamma. So this language is just something that one needs a little bit of time to get used to. When we say random length of gamma, we again mean gamma, a length of gamma parameterized by capital omega. Once you have a little omega, it is going to assign for you a length to every little edge, every edge little e, and hence a length to every path little gamma. Okay. Now you can take infimum of all these guys. So the distance between a pair of points x and y is the infimum as you vary your gamma over all possible edge paths joining x and y, and you take the infimum. So this assigns with very mild hypotheses. For every little omega, you're now going to get a way of measuring distances between pairs of points x and y. And this actually gives you, for locally finite graphs, a genuine metric. So what has happened is that if you let your gamma, you think of basically your base space, capital omega, above each, you have the same underlying topological or simplicial graph gamma, except that the lengths of edges change, and therefore you have a family of metric spaces whose underlying graph is the same gamma, but the lengths have changed. And this changing length, it's basically now you can call this gadget, what is it? For every little omega, you're going to get a metric space whose underlying space is the same gamma. So all the spaces are homeomorphic. They're in fact all simplistically isomorphic to gamma. But the distances are changing. what you have, this d sub little omega, as little omega varies over your parameterization space capital omega, is a random metric. Yeah? So the language here is essentially what is happening is that you are doing geometry along the fiber, and the base along which you are parameterizing the geometry is your probability measure space. So the theory of percolation is really geometry, or more precisely geometric group theory, as we'll come to in the next slide. It's geometric group theory on the fibers parameterized by probability in the base. Good. So now this is giving you a metric, a random metric, which means a metric at every point little omega of your base space. But not just a metric, this infimum is typically going to be realized. Again, if the graph is locally finite, it is going to be realized. And so, the corresponding to d sub omega, there is a path, gamma naught, yeah, which actually realizes this distance. So, for every little omega and every pair of points x comma y, you not only have a distance, but you also have a geodesic, which means a distance minimizing path, which realizes that distance. Okay. So this letter epsilon xy is thought of as a random variable, which, what does it do? Given a pair x comma y, there is a fixed random variable epsilon xy. What does it do? It eats a point little omega of your probability measure space capital omega and spits out this geometric object, the edge path gamma. And again, this d omega xy you can think of as again a random variable. What does it do? It's again parameterized by your little omega. What it does, it eats that omega and splits out the distance. So this guy has a name, txy, that's why it's called txy. It's essentially the first, it's called the first passage time between x and y. So think of again at the example that we started off with initially, you're splashing water, and then there's this whole sample space of the experiments that you've conducted, namely the number of times you've splashed water, and for each such experiment, you've measured a time of passage from your initial point to the final point. Basically, you've splashed water at a particular point, and say at the corner of the room, you measure when the water first reaches there. Yeah. So basically the sample space or your probability space is this collection of experiments that you've conducted, maybe with the uniform distribution if you like, and what this is measuring is for each of these experiments, it's measuring a time of passage. That's why it's called a first passage time between x and y. Classically, it was studied. Classically, this was studied for Z2, and with a little bit of effort, this is a model of percolation. So percolation was started with Z2 and Z3 way back in the 50s or 60s thereabouts by Hammersley and Welch, and a lot of effort and time was spent in studying it for ZD, yeah, Euclidean ZD. What does ZD mean as a metric space? That's what we'll come to in the next slide. But essentially, for the time being, just think of this as Euclidean space in which you are doing this. All right? So essentially, in the probability literature for a very long time, the assumption on the graph was that it was Euclidean. Essentially, there's a natural metric associated with ZD. That's that deterministic metric randomized using this model of percolation was what was studied. So, the classical model of percolation was random Euclidean geometry. Yeah, that's the way you can think of it. Now we'll come to what is the natural geometry on Zn, and that's what we'll study now. And instead of studying what Euclidean geometry is, we'll study what hyperbolic geometry is. And so let me give you a quick resume of what hyperbolic groups are. So here's the thing. For the special case of a probability distribution which assigns mass concentrated on the length 1, which means what? With probability 1, all the edges are of length 1, which means what? Essentially, you have a single graph, all whose edges are length 1. This is what is called the deterministic setup. The lengths are determined ahead of time to be 1. Basically, this gives us a classical structure, classical metric structure to each graph. What is the length of every path? You just look at the sum of the number of edges. You count the number of edges occurring in the edge path. That's the length of an edge path. And then the shortest path, which has the smallest number of edges, is what minimizes, is a geodesic in this particular metric. Now we want to, so this is essentially the notion of a metric on a graph. Now we'll start specializing to graphs which have a certain measure, certain nicer structure, namely the structure of a Cayley graph, which comes from an algebraic, which is inherited from an algebraic structure, namely that of a group. So you start with a group G with a finite generating set S. And the vertex set of the graph is just given by the elements of the group. The edge set is given by pairs of vertices which are separate, whose difference G inverse H belongs to the generating set. So this is the sense in which Zn or Z2 in particular becomes a metric space. So just look at Z with the generating set given by plus minus 1. So what are you going to get? You're going to get the usual R with vertices at all the integer points and edges just given by n comma n plus 1 closed intervals. If you think of Z2 and think of the generators as plus minus 1 comma 0, that's A and A inverse, and then 0 comma plus minus 1, then what you're going to get is essentially the square grid sitting inside Z2. That's the metric space that the people who were classically studying percolation were studying. And now that Z2 just looks like a square grid on, say, a tiled floor. So if your water is going to flow only along, say, the cracks, along the edges of the tiles, those are the channels through which water flows, and that's what you're measuring. This is the discretized version of the classical percolation problem, and this has been studied. But we are going to be interested in a case where the group is not going to be Euclidean, but it's going to be hyperbolic. And here's the thing, what's a hyperbolic metric space? So we start off with a geodesic metric space. What's a geodesic metric space? It means a metric space where every pair of points can be joined by a shortest path, which means if you have 2 points x and y such that the distance is dxy, you have an isometric embedding of the interval 0 comma dxy which joins these 2 points. So this is called a geodesic metric space, which means every pair of points can be joined by a geodesic or a straight line if you like. Such a geodesic metric space is said to be delta hyperbolic if every triangle is delta thin. What does that mean? Oh, by the way, I should say that if you have any questions, so the problem with Zoom talks is that one ends up finally feeling that one is just talking to oneself. If you have any questions, please feel free to interrupt me at any stage. So,
Sir, so
go ahead.
So why do you only work with for locally finite graph? If it's locally infinite, then just to get a geodesic.
Sure. There is going to be a bit of a problem with locally infinite graphs.
Okay,
what is the problem with locally infinite graphs? Just take a pair of points and join them by infinitely many edges.
Yes.
And now you assign lengths 1 by n to the nth die. So the distance from between them is 0 and it's not realized. So these are problems that arise as when you want to study locally infinite graphs. In the general setup that I have described, you can certainly do that. On the other hand, the kind of spaces that we are interested in are things which are equipped with a lot of symmetry, namely this group structure. So the Cayley graph, actually the group G acts transitively on the vertices. Plus, if you have a finite generating set, the point is that even finitely generated groups are not classifiable. So you have a very rich class of metric spaces coming up here. I mean, it turns out that hyperbolic groups are classifiable in the sense of, in a certain formal sense. We won't get into that. But I mean, it's a very rich class. and it's a very rich class. I'll say a little bit more about what kind of groups these are. So group G is hyperbolic.
So another one thing. So
yeah, go ahead.
If we vary small omega over capital omega and
Yeah.
script omega, so then we are getting different kind of spaces. So I mean,
So I haven't put these two pieces together yet. So the first slide, what it did was it allowed your little omega to vary over your probability space capital omega. Yeah.
yes, sir.
That is what defined percolation. Right now, I am defining hyperbolic groups. Once I say a little bit about hyperbolic groups, in the next step, we are going to put these two pieces of the discussion together and we'll say what percolation on hyperbolic groups is. So I'll come back to your question, but a little later.
Okay.
Is that okay?
Yes.
Okay, very good. So now, what does it mean to say that a group G is hyperbolic? See, a group G is just some algebraic object. And now we are claiming that it has some geometric structure. Where is that? It's true provided that the Cayley graph, or so that a Cayley graph with respect to some finite generating set is hyperbolic, which means it is delta hyperbolic for some delta. And a fundamental theorem due to Gromov basically says that if it is hyperbolic with respect to some S with some constant delta, with respect to any other finite generating set, it is also hyperbolic, maybe with a different delta. So maybe something is 10 hyperbolic, and then you change the generating set and you become, say, some 57 hyperbolic. That's okay, it doesn't matter. The point is, it's only the large scale structure of hyperbolicity that is going to be of interest to us. And here's the fact: such groups are ubiquitous. They occur all over the place. Yeah, one of the simplest things, it's sort of essentially, if you look around you, I mean, the metric space underlying trees are exactly, these are exactly hyperbolic metric spaces. Yeah? These are zero hyperbolic. So if you take a tree, I'll come to that in the next slide. So for now, let me just say what is the problem? You have this rich class of hyperbolic metric spaces. Now what you want to study is randomize this. Essentially, this is the deterministic setup. Just as percolation studied random Euclidean geometry, question is, what is random hyperbolic geometry? And the way of making it precise is to study first passage percolation on hyperbolic groups. Okay? So now I think I've returned to your question. So we try to make this precise. What does first passage percolation on hyperbolic groups mean? It means that the graph that you're considering is the Cayley graph of a hyperbolic group. Yeah. So that gamma that we started off with is some fixed group gamma, a fixed graph gamma, but the lengths are varying according to this probability distribution, which assigns the lengths to each edge independently according to some fixed probability distribution rho. So you have choice. The choices are two. One is, what is the probability distribution rho? You can impose some restrictions there. And the other thing is, you can choose your hyperbolic group gamma. And the point of this talk is that for a very large class of rho, there is some uniform collection of properties that these guys have. Okay, so let's come to that. So here is an example, some examples of hyperbolic groups. Yeah. So these are examples of Cayley graphs of hyperbolic groups. So essentially, yeah. So the picture at the bottom, yeah. This is the picture at the bottom is a 4-valent tree. So essentially, this is the free group on two generators. There's an A, there's a B, and there's opposite side. There will be an A inverse and there will be a B inverse. So all formal words in A, B, A inverse, B inverse, with the only restriction that A is not followed by A inverse, B is not followed by B inverse, or vice versa. A inverse should not be followed by A, B inverse should not be followed by B. What are you going to get? You're going to get this picture of a tree. Yeah. So the tree where every vertex has valence 4. Now this, it's easy to see, is actually a zero hyperbolic space. Why? Because you start from any point, then you look at the geodesic joining any 3 points, and that's actually going to look like a tripod. Yeah. So the letter Y, let us say in English. Yeah. So each side, each edge of the triangle is actually going to be contained in the genuine union of the other two sides. So it's a zero neighborhood of the union of the other two sides. So a tree is an example of a zero hyperbolic space. So this gadget is hyperbolic. Another thing that you get, these are these pictures at the top. These are essentially more given from tessellations of the hyperbolic plane, which is essentially the unit disk equipped with the metric, something like 1 by 1 minus r square whole square, multiplied by the Euclidean metric. Yeah, so that gives you essentially a constant negative curvature metric. So these guys are classically what were known, I mean, as discovered by Gauss and Bolyai and Lobachevsky, of what was the model for the two-dimensional hyperbolic geometry. That's why we call this hyperbolic. Okay. So if you look at the graph, which is dual to this tessellation, that graph is an example of a hyperbolic graph, and there's a group associated with this symmetric tessellation. There's a way of tiling. There's a group that encodes it. So the dual graph of this tessellation that you have, or this tiling that you have, that dual graph is also a Cayley graph, and that's a hyperbolic graph. Okay, so these are the kinds of graphs on which we want to study percolation. That's the problem. Now, are the questions that were addressed, or are there some other questions? So that before I start saying what we have, I should address the questions now. Are there any other questions? Okay, fine. Yeah, please feel free to interrupt me whenever you like. Yeah. Okay. So now here is this crucial thing, that is a difference between the Euclidean setup or the continuous Euclidean setup and in this particular setup. What happens in the Euclidean setup is that if you're not working on a graph, but if you're working on, say, the Euclidean plane, then every point has a tangent space. Now, once you have a tangent space, you have a unit circle. Say, let's say we are thinking of R2. So you have a unit circle. So that circle, that unit circle measure is a way of parametrizing tangent directions. Now, what about a graph? A graph, if it's just finite, there are just finitely many directions at a point. So this infinitesimal notion of directions is not going to help us in the graph situation. So what do we need? And here this is a fact which is basically of hyperbolic geometry. The key feature of a hyperbolic group is that it has a boundary at infinity. Essentially, so if you think of the Euclidean plane and you look at the various tangent directions, and you take, say, two directions and then you extend those directions to geodesics going off infinity. The two rays which are going off to infinity are never going to meet again once they start diverging from zero. Yeah. Which means that there is a bijective correspondence between the infinitesimal directions and the directions parameterized by directions at infinity. Essentially, the circle at zero, which is the circle of tangent circle, which is a circle, say, of dimension 0 or an infinitesimal, is bijectively in one-to-one correspondence with the circle at infinity. Yeah. So directions at 0 are in one-to-one correspondence with directions at infinity in the Euclidean space itself. The Euclidean space is not hyperbolic, but this particular feature of bijective correspondence between infinitesimal directions and directions at infinity, this bijective correspondence is essentially known as the Cartan-Hadamard theorem. It is a feature of spaces which are non-positively curved, which means that the curvature just needs to be less than equal to 0. The Euclidean plane or Euclidean space has curvature 0, and these hyperbolic things that we are talking about have morally curvature. I mean, they have this large-scale property that they share with spaces which have curvature strictly less than 0. So strictly less than 0 is a part of less than equal to 0, and the Cartan-Hadamard theorem applies. But since we are in a graph, we can't quite do that. However, this part of the Cartan-Hadamard theorem, you can at least get the proof out of it, and you do get a boundary at infinity. So this is one of the things where you have to invert your viewpoint, and instead of thinking of directions as parameterized by infinitesimal things, you use the space at infinity to parameterize directions. Good. The thing is, the Euclidean circle also has a natural measure, namely the arc. I mean, the angle subtended at the origin, that is a certain natural measure that is that you can equip the circle. What about the boundary of a group? And that is essentially, there is a measure which is called the Patterson-Sullivan measure, which is morally speaking, you can think of it as the weak limit of uniform measures on balls of radius n. What's going on here? Essentially, these hyperbolic gadgets, they increase very fast. And so the boundary has a lot of the measure, and if you weight it appropriately, what happens is that if you add the boundary G to the Cayley graph of G, you get a compact object. Now we know by Banach-Urlu, the collection of probability measures on any compact metric space or compact metrizable space is compact. So if you just look at uniform measures on balls of radius n, and then you let n to infinity, what happens is essentially the support of this measure pushes off to the boundary, and the limiting measure is supported on boundary G. Good. So now we have two probability measures in the game. One is this Patterson-Sullivan measure, which we just talked about. So when we are going to say almost every with respect to direction, we are referring to Patterson-Sullivan measures. But when we are referring to say almost every little omega, then we are referring to this little omega in your parameterization space. Yeah? So these are the two things that you need to keep in mind. So what is it? So you're going to have your Cayley graph of the group G, that's your gamma, parameterized by your probability measure space capital omega, and you're really going to parameterize directions by the boundary of this gamma, which is boundary of G equipped with the Patterson-Sullivan measure. All right, fine. Now let's come to statements of the theorems that we have. So here is the thing. See, basically, you look at, say, a sequence of points going off to infinity in a particular direction. Now you join those points to your origin by your random geodesics, which means what? It's going to be just a collection of paths which are parameterized by your little omega belonging to capital omega. A priori, you have no idea whether this is going to be close to the straight line, close to the geodesic, how far it's going to deviate from the geodesic, etc., etc., etc. Right? So the first statement, first theorem that we have is basically saying that, look, the random geodesic ray does not deviate too much from the deterministic geodesic ray, which means essentially it has the same direction as the deterministic geodesic ray going off to infinity. To make that precise, what you say is that you have a path sigma, just a path now. It is not a geodesic in the deterministic sense. It's just an edge path in the group gamma. You say that it starts at the origin O. You say that it has direction xi if the only accumulation point of this path in the boundary is the singleton xi. And here's the theorem. Basically says that given you fix a direction xi and you choose a sequence of points xn converging to xi, then for almost every little omega belonging to your probability measure space, the random geodesic 0xn omega from 0 to xn, it converges to a ray. Forget this up to a subsequence, that's not very important. It converges to a ray. Ray means just a path, yeah, a sigma, path sigma, which has direction exactly xi. So what this theorem says is that now you can randomize your metric and you can look at the geodesic ray for xi, for this little omega, and you look at the collection of accumulation points on the boundary. Yeah. So essentially, what is the kind of phenomenon that you want to rule out? You want to rule out that it oscillates between 2 points. So you do have points which go close to one point at the boundary, then go away from that and go to another point, close to another point on the boundary, then oscillates back to the first point, then oscillates back to the second point, and keeps going between these two. Yeah, it can't intersect itself because that then would not be a shortest path in any metric, but it still can come close to two different points. What this is saying is that such a path can almost surely not be an omega geodesic, provided omega has some very, very minimal assumptions. Is the statement of this result clear? Yeah, I mean, somebody please respond.
Yes, it's clear.
Yeah,
Okay. Very good. All right. So this just says that the directions, the random directions of geodesics exist. Fine. And what about the actual velocity? How about the actual speed of going there? So for that, we need to define speed. That's the next result. It says essentially that velocity exists. Actually, it is constant almost everywhere. What does that mean? So here is the thing. So you have a random variable. Recall that you had this random variable txy. What was it doing? It was eating a point of your probability measure space little omega and was spitting out a distance, right? So txy is a random variable, measurable function, equivalent to a measurable function on the probability measure space capital omega. So since the base space, the parameterization space is a probability measure space capital omega, you can, it makes sense to say what the expected passage time is. You just integrate this random variable over the probability measure space and you get your expected passage time. Yeah. So txy is the random time of passage. E of t is the average of the random time of passage. Fine. Now we want to define a velocity in a direction xi. So for xi, you define the velocity in the direction of xi to be the following quantity. It's the expectation of the random time divided by the deterministic. Deterministic means in the base graph. Yeah. So it's random time by deterministic time. Yeah. And then what about what was xn? Xn was just a sequence converging to xi. Yeah. Just a sequence of points which converge to xi in the compactification. And you say that this limit is equal to the velocity under the crucial condition provided this limit exists. A priori, there is absolutely no reason why the random time divided by the deterministic time, the limit should exist. And so here, we introduce our first condition on the probability measure space, and we basically say that rho does not have any atoms at the origin, yeah? Which means that the measure of the point 0 is actually 0. And this is another class, basically it's what are called sub-Gaussian distributions. Essentially, there exists some a greater than 0 such that the expectation of e to the ax square, this particular e power, this Gaussian looking thing, e power minus x square is essentially Gaussian. So this is going to be something like e power minus bx square is what you want rho x to be. Yeah, so if it's some Gaussian, if the integral of e power ax square for some a greater than 0 is less than infinity, you say that the probability distribution is sub-Gaussian. So you assume that the probability distribution is sub-Gaussian. This is not an optimal assumption. There certainly is true under much weaker assumptions, but we just wanted to get some geometry out. Okay, very good. And so what we prove is that for almost every, and here is the crucial thing, that even for the free group, this is, you can't quite upgrade it to every. So here is the statement, the velocity actually exists. Yeah. So the velocity v xi in the direction of xi exists for almost every xi belonging to the boundary. Note that this for almost every is with respect to the Patterson-Sullivan measure. Now, there is a certain phenomenon called ergodicity, which essentially says that the oh boy. Okay. So the group G that we started off with, here is a certain special thing about hyperbolicity. The group G actually acts on your boundary. Yeah. And that action on the boundary, so with respect to this Patterson-Sullivan measure, the action of the group G on the boundary is what is called ergodic, which means essentially that there is no subset of measure other than 0 or 1, which is left invariant under G. If you have a G invariant subset, it's either a full measure or a zero measure, which means that this velocity, which is a measurable function, it's an immediate consequence of ergodicity, that any measurable function necessarily is constant. So this, it turns out that in the hyperbolic case, the action of the group G on the boundary is ergodic. This is something that's very, very different from the action of Z plus Z on the boundary circle of R2. There, Z plus Z actually acts on the boundary and leaves every point fixed. So every function is actually invariant under Z plus Z. Here, it's completely opposite. Basically says, I mean, that was sort of the maximal collection of measurable functions that is left invariant in the Euclidean case, and in the hyperbolic case, it's minimal. Essentially, it says only the constant functions are left invariant. Yeah, and so this velocity v xi, but it's only in a measurable sense. So this velocity v xi is constant almost everywhere. Yeah? So you have two things: velocity exists in almost every direction, and the velocity is constant in almost every direction. And the fact is that this is a genuine measure theoretic statement, not a topological statement. You cannot upgrade this statement to say that the velocity exists in every direction, nor can you upgrade it to say that velocity in almost every direction is constant. Yeah. So this is the best one can get, and essentially the free group with a slightly modified set of generators gives you counterexamples. All right, this is the second phenomenon. I think I have a little bit of time left. So it's up till 5 o'clock, right?
Yes, yeah.
Okay, very good. All right, so this is the second statement. Now we come to some slightly finer properties. So this was about geodesics all of them starting at your fixed base point O and going towards a particular point xi on the boundary. Good. What about a pair of points? Suppose you have two base points, yeah, O1 and O2. And you start off your percolation from both these points, but you are going towards a single point xi at infinity. What happens to a random geodesic? And this brings us to the phenomenon of coalescence. What is coalescence? You say that two semi-infinite paths, sigma 1 and sigma 2, you say that they coalesce if beyond some point they actually coincide, which means what? Two fellows start 1,000,000 miles apart, they travel say 20 million miles, and then they hit the same point. Yeah. So basically, two people who don't know each other come and meet at some point after traveling for a long time. And then after that, they travel on the same path till infinity together. This is basically called the coalescence of two paths. Yeah. And this is exactly what happens to random geodesics. And here the quantification is a little bad. What you should, let me put the statement on the slide and then correct the quantification. Fix O1, O2, these are two base points. Fix a direction xi. Yeah? So the geometric information is now a given to you. The two base points you start off with and the point xi on the boundary, that's also given to you. Then for almost every little omega belonging to your probability measure space, the geodesic rays from O1 to xi and the geodesic ray from O2 to xi measured with respect to the random metric given by omega, these coalesce. Yeah? Which means what? Which means for almost every point of your probability measure space, if you give me these 3 points, O1, O2, and a point on the boundary, these two fellows, the geodesic rays, will come together and proceed together for all eternity. Yeah, they will come together after some point, and after that, for all eternity, they will be there together. Clear? Yeah? Okay. I mean, have people understood the behavior of this coalescence? Yeah? Just somebody please just say.
Yes.
Yes.
All right. So now we come to the last theorem, and I think I'll just have a time for the statement of this. We won't be able to get into proofs of anything. So what was the passage time? We basically said that the passage time divided by the deterministic time T1xn. Yeah. So basically T1xn. So let's say for simplicity, you take a deterministic geodesic from the identity 1, yeah, the base point O that we were referring to in the previous slide. Now we replace by the base point 1, yeah, and then look at a geodesic ray in the deterministic graph, yeah, going off towards a particular point at infinity, namely psi. Yeah. Then what you can do is you can just look at the passage time from 1 to xn and then let n tend to infinity, right? So T1xn, what we proved was that T1xn is actually equal to, say, something like v times distance 1 to xn, where v is your velocity. That was the second theorem that we mentioned for almost every side. So now, since we are interested in only the probabilistic thing, it's enough to look at almost every side. So T1xn was divided by D1xn was going to converge to a particular number v. So this is sort of the first order behavior of this random variable passage time t of 1xn. The expectation of this, expectation of T1xn, is actually equal to some little v constant times the distance between 1 and xn in the limit. This is what we had proved. Now, as soon as you have the first order behavior, final question is, what about second order behavior? So how do the variances of these random variables behave? Yeah. And here's the thing. You look at these random variables, T1xn, you know that expectation of T1xn is approximately some constant times n. Yeah. And if you look at the second order variation, the theorem basically says that it actually increases definitely, but only linearly with n. So the variance of this random variable T1xn is bounded below by some constant C1 times n. It grows linearly, and it's bounded above by C2 times n, which means it at most grows linearly. So basically, we don't have a time bound, but it basically means that we can bound this variation between two linear functions of n. Yeah? This particular thing was actually a conjecture of Benjamini and Teixeira, who were the first people to start studying percolation on hyperbolic groups, and this conjecture is resolved by this thing. So I think I'll stop there. So these are the 4 main results. Thank you.
Thank you very much, Professor Mahan Maharaj, for this excellent exposition. And it's time for interaction. Please put forward your questions, comments, suggestions.